Okay, once again, for those who might have joined online, I hope the sound is fine. You can join on Slido, as you can see on the screen, or you see it on the right if you open it through the link on the website anyways. It's a good way to count how many people are in the audience, unless people have trouble joining. Is anyone struggling to get on the poll? If that seems to work, then we're just shy of 60, which is half of the sign up on Elias so far. But the regulars might know that we never start before quarter past. And so we'll see. But if everyone showed up who was registered on Elias, it would have been really crammed in the room. That's why my little panic email in the morning. However, most of the time, people register for more lectures than they eventually can and want to continue with. Right, so it's quite normal. Also, sign up on Elias is just a click. Showing up at 10 a.m. is a different story, so we'll see. I hope I'm loud enough. I don't think we have a mic, even if I wanted to use it. So you'll just have to be nice and quiet, like now. Let's do something more interesting than this question, where obviously a few people have made up their mind and the other half is still looking into this, which is totally fine. For this module, a particularly relevant question is what you bring as background, and specifically theoretical computer science of some sort, by which I mean a module that covers automata theory and formal languages and computability or decidability. That's the usual Triforce in that undergrad module. It's widely spread. I think all German universities I've ever seen that offer a computer science degree will have such a module, but not everyone has done a computer science undergrad. Not everyone studied in Germany, so I think the question makes sense. It's not a formal requirement in the sense that you're not allowed to take the exam if you haven't done this module. It's a prerequisite by the contents, so you can catch up on this. It's up for you to decide if you feel it's working fine or not. If you've done such a module, hopefully some things will sound familiar, what we do this week, and then you'll get up to speed quickly. I'll go through some of the material that will normally appear in such a module this week as a recap, and also to set some of the definitions and notations to have one specific set to refer to. There's always some variations in how things are taught. Another cool feature on Slido is that you can ask questions. And there's one question that popped up there. So the question is, in terms of the overall content and the complexity, how does it compare to efficient algorithms? Efficient algorithms has the same number of credit points as 9 LPs, so the overall workload should be similar. That said, efficient algorithms is an undergrad module, so I should have marked this that we're talking about this question. Efficient algorithms is an undergrad module, so it has different prerequisites and different assumptions on your efficiency. So for an MSc module like this one, you're probably expected to work a little harder than for the undergrad ones, but that's all relative to where you come from. Otherwise, the amount of content should be similar. In terms of the complexity, that's again, is a bit hard to say depending on where you come from. They're not directly related, they're kind of separate. Efficient algorithms is all about the problems in P that you can solve efficiently, and then how to do it real efficient. Whereas this module is about the problems that seem hard to do anything intelligent. What can we still do? What can we prove about them in terms of hardness, reductions of that sort, complexity theory? So in a way, it's just different. So you can certainly ask questions here. I haven't made up my mind what the final assessment will be. I'll give that a little bit time to see what the enrollment is. The default for MSc modules would be an oral exam. If it stays at 120 people, I think that's just not going to be a nice experience for everyone involved. Like for me doing all of them, but for you also finding slots will get tricky. And by the time I hear the content the 100th time, I don't know in what mood I would be. So if it stays at that enrollment, it would be more of a written exam. In either case, there's no past written exam to refer to because it's been done with oral exams in the past. But I can dig out some old protocols from what I would have asked. I've taught a similar course a couple of years ago in Kaiserslautern, so that's what I would compare it to. It's the first time I'm offering it in Marburg. But we'll look into what we do for the exam. You ask piercing questions that I was trying to avoid for a bit. Yeah. I would say we hold off with that question a little bit until you had a fair chance to see what the module is like, and you can make up your mind whether you continue it or not. Okay, mic is too low for YouTube. I'm a bit concerned if I bump it higher, then it gets into getting too loud. The recordings I always normalize a bit, so the loudness is better. Can you hear? Maybe you can ask another question. Tell us if you can hear at all or if it's just a little low. So for the record, this is, okay, 41. We had something just shy of 60 last question. So if you haven't answered on this one, you can do. Okay, just low, then I'll test it again if I can bump up the setting, but not now because the recording will otherwise be screwed up. Making that a bit louder is easier in hindsight, but if it's too loud, it won't work. Yeah, so that's the website, or the old lecture notes you can find on this old website. It's not the exact same slides I will use. I've updated them and switched out a few topics. The rough outline will be similar, but the details will be somewhat different. There'll be some overlap between the modules, but I'll try to be a good boy and put up slides ahead of class, which I failed on for this one, because the first part is a part where I've changed a lot, because the module back then could just straight on continue from a specific module that everyone had in this audience there. So I could rely on precisely the definitions that everyone was getting from their previous module. So I've substantially added to this. That's why it's not ready. In the future, there'll be some slides on the websites, which I could potentially show. But you probably found the module website. There will be subpages for the units where you can find the slides. $43. We're waiting for the other 20 or 15. Yeah, Slido updated their interface. It looks entirely different on my side now, and I'm not overly happy with how it looks. So I'll try to peek to my phone a bit more often to see if someone asks a question or so. If you ask questions during the lecture, I might sometimes just delay answering them. But if you feel like, oh, I overlooked something and it would be more useful to answer it now, you can always make me aware. Okay. Let's properly start the lecture with some organizational bits. I've always tried to group the lectures into units that cover roughly 1 week. That's not exactly true. In the first ones, we'll actually cover 2.5 units today. So the first ones are shorter. Others will be a bit longer. But that's a rough guidance. And also I'm trying to structure the content that way a bit. So welcome to Advanced Algorithms. In the first part, we'll just talk about some organizational bits. I'll go relatively quick, but I wanted to have this on record so that it's there to refer back to. The goals is to show you how the module is run and how it's assessed, and then the follow-up little unit will give a bit of an overview of what it is about. I'm Sebastian Witt. Wild is fine if you prefer. I'm occasionally sitting in my office up there. Best if you want if you need something, best is fire an email or use CampusWire for things that are specific to this module, especially if they're relevant to other students. I'll come back to that. We'll have Mohammed help us in the tutorials. We'll come back to what happens there. The most important piece of information is the module website. If you haven't run across it, that's where you find all key information. I'll try to make everything that can be on a public website onto this public website. I just find it myself so much more convenient not to have to log in every single time you look up some little bit. I feel this is also helpful. I didn't at all copy paste the slides. Other bits that we're going to use are CampusWire, which is a Q&A forum. I'll explain a bit more what this looks like, but you can already sign up. The join link is on the public website. The link and the pin is on Elias, but it's also here if you want to do that later. Slido you already saw what we use it for. And as a rough summary, as we're forced to do it like this, the final mark will come from the final assessment, whatever that is, and that's it. There's no way to do partial marks in an easy way, but you have to earn the admission to the exams via points in the exercise sheets and the mini seminar that I'll comment on later. We've seen Slido already, so you know what it feels like. I just want to motivate a bit why I'm using it. I feel it's a very helpful psychological little trick to activate people from time to time. Otherwise, it's easy to fall into the mode of watching TV, which is fine, but sometimes is not as effective for learning something as other modes of listening. It also gives me a little bit of feedback whether you're following along. That's helpful for both of us. You've seen what it looks like. That's polls, which is I push a question out to you and you get to answer, usually multiple choice, and you can answer a question. You can ask questions on the audience Q&A at any time in between. If it's hidden because there's a poll running, you can still switch the tabs. I hope it's intuitive enough. Let's skip this because we've done an intro question already. In all my lectures, there's always the question, how do you organize lectures in general? And many of you will have had the dubious pleasure of having to do studies during the pandemic, where everyone was forced to do some experiments with alternative modes of teaching. I've actually done my experiments with alternative modes of teaching well before then and concluded I don't like it, at least not pre-recorded videos and then flip teaching, where I send you off to watch videos and then we meet and discuss afterwards. I just couldn't get it to work. And that might be my fault, but I always felt it's very hard, also if I'm experiencing this myself, to stay on track with the lecture if you're not forced to synchronize at specific times. So that's what we'll do. We'll have synchronous live lectures, but I give you the option to watch them from your couch at home if you feel that's helpful for focusing, or if you can't come for some reason. And if you can't make it at all, there's recordings which are not interactive, but at least you can still catch up what we've covered. And you can rewatch if your memory is fading. Now, if you want to do anything interactive, there needs to be something coming back from the audience to me. And the traditional way would be some students occasionally ask questions, and you're encouraged to do that whenever you feel that's helpful. My experience is only a very small subset of students do that for many reasons, and that's fine. So I'll always try to have other back channels. There's Slido for questions, which you can use during the lecture, and Campus Wire later. And little polls in between just to keep you awake. I've covered most of this already. So we have lectures, and we'll have these Slido questions, and we have Campus Wire. More on this. I keep referring to this. We'll come back to this. We'll also have some tutorials with exercise problems. Many of the topics that we'll cover only really get understood by doing it yourself, by proving things yourself, by designing algorithms yourself, and by doing reductions yourself. So there will be handy-in exercise sheets. These will only start after the mini seminar, which should be here too, together with the tutorials. Let's add it. The exam, of course, in the end is a requirement. And I'll do this experiment again of having a collaborative exam question gallery where you can collect possible exam questions. And the more work you do there up front, the more I promise to comment on those questions. And we'll see how that goes. My experience is if I tell you to do this now, nobody does, because you haven't learned that much in this module. So I'll reopen this a bit later in the term, try to raise enthusiasm for it when we get to it. Let's talk about assessment briefly. As I said, the actual points you get at the end come from the final exam. That's the only option you have, the only option we have. I'll announce soon whether it's written or oral. And the material that's covered in either of those forms of exams is everything that we cover in class, except maybe sometimes I feel I'm making comments that are useful if you want to go into researching this further, but are really a bit over the top. Then I'm sometimes marking them with not part of the exam. Anything else is covered. And also the tutorials and exercise sheets, because these are often complementing what we do in class. So they're part of the exam material. To be admitted for the exam, we decided to set the rules so you can skip up to 2 of the exercise sheets. Might be a lot because I'm planning to do them bi-weekly instead of weekly. But I'll let you know. And 50% of the available points, but the marking will be mostly rewarding genuine attempts, not only completely solved. And the last bit is a little extra thing we'll do over the next 2 weeks. That's the mini seminar on NP completeness. So because the group is a bit diverse and you come from different backgrounds, much of the later parts of the module really don't make sense if you don't have a solid foundation in the classical complexity theory, NP completeness. And I can, of course, run through this here, and I'll do that this week. But to make sure that you have a chance to grasp this, you'll have to do something from your end. And so what we'll do instead of lectures the next 2 weeks is a little mini seminar where you prepare in groups one topic from NP hardness and present it in two forms. So again, the goal is to make sure everyone's on the same page with respect to NP completeness before we move on. And it's a master's module, so you're supposed to go towards the cutting edge of research. Now, we'll do this with a very old research paper, so cutting edge is not a literal term here, but it's still primary research literature, which is always a bit of a different type of reading. If you read textbooks, everything has been pre-digested a few times before it's presented in a way that the author thought at least is most useful. Primary research literature is often a bit more rough and concise. So it needs practice to read those, and that's one way to do it. And same as in the exercise classes, I want you to be able to write proofs in a way that is rigorous. And so that's another way to test that. So what you'll do concretely is make a written report of one NP hardness reduction. And we'll pick some classic examples where it's not incredibly hard to find material online where people already explain this. But the point of the whole mini seminar is that you put this in your own words and you dig through this one example very deep. So one deliverable is the written proof. And it should be the general construction plus a fully worked example for the two cases that you always have in NP hardness reductions, a yes instance and a no instance, just to make 100% sure you understood the construction. You'll have done some of this in a theoretical computer science module if you've done one. But hopefully not exactly the problems that are on the list. And I think it's a good refresher before we move on. The second bit, maybe the bit more fun part, try to make a nice explainer video out of this. So this first, the written report should be completely formal, mathematical language and formulas and all that. You're very welcome to use LaTeX for that. If you feel a different system is better, that's fine. The second part is a bit more conversational and is just supposed to make it easy to understand your construction. So in a way, your video could be a high-level introduction to your report, so that if someone wants to dig into the details of the proof, they can watch the video and get the gist of it, and then see the full details in the report. And so that these videos are not write-only documents. Each group will also watch over the video and the report from 3 other groups and write a little report just summarizing how well it worked for them to understand the reduction. I'll send out some specific guidance. This will be very narrowly guided, so you don't have to write a lengthy essay how you liked it. It'll be specific guiding questions. But I think it would be a shame if you make nice videos and then nobody sees them apart from us. So the goal is to have this over roughly weeks 2 and 3. And my original idea was to pick the original and first and only paper where NP completeness was introduced. I don't know if you know the story behind this. This was, when did he publish? I think it's 1973, 73. It's certainly early 70s, but don't quote me on the year. And also, I guess the results were known a bit before, and then it took a while to publish. Richard Karp published one paper that I have here in nice typewriter, where he invented the idea of NP completeness and gave 21 NP complete problems, where for most of them he just lists very shortly, very briefly the construction. And he doesn't even bother to spell out the correctness arguments, why the reduction works. So the goal would be to pick, these are 21 problems, but it's really just 20 reductions, because one of them is Boolean satisfiability, which is separately proven. That's the Cook-Levin theorem. If none of this makes any sense to you, by the way, it will after the end of tomorrow's lecture. I'll go over the basics of this at a crazy pace, but so that at least if you haven't heard anything about this before, you'll know your basic way around. So there's 20 reductions in there. If we stay at 120 people, that would be a bit big groups. If we are roughly of the size here, it might work out. If we don't cover all problems, that's also fine. But I think group sizes beyond 5 people is getting tricky. Yeah, I have a website prepared with more details on how this is going to run. But if you have specific questions now, let me know. There's one question also on Slido. No. You can see. It's part of this module. That's why I call it a mini seminar. It's not as much work. You're in the master seminar that also exists. You're usually reading full papers and maybe several of them and compare them, something like this. And you do it alone. So here we have 3 to 5 people working on it. And the part that you have to read from the paper technically might be something like just a single formula or so. Many of the reductions in here are really, really short. You'll probably have to read the definitions to understand them, but it's far less intense than the seminar modules. Other questions about the mini seminar for now? Okay, let me go back. There's one thing we haven't talked about, which is CampusWire, but okay, tutorials first, that as well. So formally, the mini seminar is part of the admissions for the exam. You'll do a few less of the exam exercise sheets. You'll do the mini seminar instead. And those two things together are the admission requirements. I hope it's not supposed to be a super overwhelming task. And the videos can also be low fidelity. So essentially have someone film with a smartphone while you write on a piece of paper is not a stupid idea for a theory thing. I've seen that done with pandemic time tutorials, and it was super effective. It doesn't need to be any flashy animations, although if you want, you're welcome to. After, should probably put this here somewhere. We'll start with this after the mini seminar. More traditional exercise problems on a sheet that you hand in a group, as most modules have it in some form. So that's what we'll do as well. I'll probably have the pleasure to present some solutions to you in some central exercise tutorial. But we'll have to find a room for that. So again, because we only start after the mini seminar, I'll delay the decision depending a bit on how big the audience still is. As I mentioned before, we'll be a bit more lenient on the marking because the intention of more lenient than in an exam. The intention is to get you working on problems. While we talk about exercises, I noticed there's a new thing around, and you noticed too. It's amazing fun to play with all sorts of, DeepSeek for these kind of problems, theory problems, is pretty useful. I wouldn't say it kind of solves anything without guidance, but it's useful as a research tool for sure, and for many other things. What it doesn't do is help you learn. Quite the opposite. And if you take a step back, why are you doing this? All of this, like your degree? Why are you studying here? Maybe there's many reasons, but hopefully one good one will be that you take skills out of this that help you in your career, set you apart from maybe other people who haven't invested the same amount of time. All of this is kind of compromised if you let some AI do the work for you, specifically for these exercise problems. They're designed for you to help you acquire skills. So don't cheat yourself by taking away the thinking. And I'm not even saying that we try to catch you cheating. That's not my point. If you're smart about doing it, you won't be caught because you let AI make suggestions and you just rewrite it in some human form. I'm never going to find out, but you're also never going to get the skills that you wanted if you don't bang your head against the problems for a while. I know it's very tempting. It's pretty hard, especially if time pressure ramps up. But try to remind yourself of just not doing it. Is similar to, that's why I put this quote here. It's a bit of a jokey quote, of course, but the point of doing exercise in a physical sense is also not to be 10 kilometers away. If you run in circles, for sure not. It's about what you get out of the exercise. And if you let a robot do the same thing, or if you drive by car, it's not the same, right? Okay, enough about that. Just to be very clear, it's acceptable to do preparatory research. So replace Wikipedia in a sense. Use it as a point to jump to the right place to then read more. That's fine. I'm also fine if you use it for proofreading your writing. It's always nice to read well-formulated text. Don't use it to generate whole parts of your submission without proper acknowledgement, citation, and so on. Don't use it to make something that you took from somewhere else sound different so that you're not caught. It's obviously ethically problematic. And also avoid letting it do all the thinking for you. Okay, I should have prepared this one. Let's do this quickly because I think this is a key question. So you can think about this while I'm setting up Slido. What I'm looking for here is a criterion self-reported from students that had the strongest correlation with them also cheating on assessments. So there was a specific thing, interestingly striking how much it stood out, that correlated well with also cheating. Now it's correlation, not causation, but I think it's still an insightful thing. So have a guess. What do you think? Of all, I mean, it could be personality traits, it could be habits, it could be, demographics, gender, whatever. It could have been. Thankfully, that is not what it was. It's a good point that cheating can become a habit. But the point here was there's something that correlated with having the habit. Not going to class, not studying. Work perfection is an interesting one, yeah. Yeah, language, I mean, barriers of all sorts don't help. I'm reusing the poll from different lectures, so maybe someone remembers. The right answer is among the options. Pressure in general is also an interesting one. That would have been my guess. The more desperate you are, the more you're going to cheat. But that wasn't quite true. Yeah, so the answer's among there, and it's procrastination. Students that tended to procrastinate, to not get things done in time, and not necessarily because of pressure or outer things or really like hardship cases. It was the habit of not planning and managing your time well enough that constantly led to being behind. And then, I mean, procrastinating is the process of spending your time unwisely, but it also means that you have trouble reserving the time for the important things, right? That's the flip side of it, of course. And it's interesting that it correlated so well, because it kind of seems to be the source, the root of time problems later on, and many other correlating things, maybe pressure and desperation and all that kind of flow from it. Okay, I'm not gonna be able to analyze more. This is just something. The source is given in a video where the context is explained a bit more. I found this useful to push out, just as a nudge. Get your time management right. It's another obvious one. Not telling you any news, maybe. Okay, CampusWire. I would say it's closest to Reddit before it became apparently not a nice place anymore. You can ask questions, they pop up at the top, and you can post answers, and the answers are ranked by how many people upvote them. You can reply to answers, so it has the same kind of structure. The difference in CampusWire is it's a bit more specific to the setting of a lecture, of a university lecture. So you can only sign up with your university email by default, for example. In case you're having trouble, try to use something with the Uni Marburg domain. The other feature is you can ask questions anonymously. If you don't want to expose yourself in front of the whole class, that's okay. And you can ask anonymously, also answer. But the idea is really that the whole group also tries to help out others, because the best way to learn is to teach others. It has two features that we use. The class feed is what I was speaking about. That's the Reddit-like feature. There's also chat rooms that are just a little less structured. And maybe for instantaneous things are sometimes useful. The class feed should be the standard Q&A place. If you have a question that relates to the content of the material, or also organizational things that are not super urgent, the best is to put a question out on CampusWire, because then everyone can see it. And I can answer it once if it's organizational, and you can try answer it for others if it's content-based. So any of these types of questions. If you found an answer helpful, then upvote for it. That will influence the ranking. And it also has a credit system, so you get some, you can climb up the ranks by being active. There's an option to ask a question privately just to instructors if you feel it's spoiling some assessment. That's the way to go. Most other things I think is fine to have public, and anonymously if you want. Right. Just to be explicit, I'm trying to push CampusWire. If you send me an email and I feel it's something that should go on CampusWire, I'll reply to your email, but I'll just say CampusWire. Okay, I'm never going to reply with an actual useful answer. But if you put it on CampusWire, if it's urgent, I usually have it quick on the phone and see it on the day. But I might not respond if it's a content question, to give other students a chance to answer. The goal is to be fair, because everyone gets the same answers, which is different if you come up after class. Then depending on how much time we have, I think it's preferable to do it on CampusWire. It helps you to learn if you can answer for someone else, and it's more inclusive if everyone as a way to express themselves, I think. As I said, I'll redirect you to the class feed on CampusWire with wherever that's the most appropriate place. I'll hold up answering a little bit, and I'll promise if someone answers the question for me and does a good job, I'll eventually put an endorsed or forget what the term was on CampusWire. But there's a way to mark it as, okay, instructor has said this is actually right. Yeah, something like that, but it's a different term, and you can assign it to several answers. So it's not like Stack Overflow. Yeah, see how you get on. First sign up, and then we'll have a play a bit, and maybe we can discuss tomorrow again if something doesn't work or if you have questions about it. There's also Elias, the official university online learning platform. I'll mostly use it for anything that cannot go to a non-university server, which is all your personal data, especially anything relating to marks. If you sign up on CampusWire with some fake name, I guess that's all right. I don't really need you to be identifiable there. Elias is different. That's where anything official happens, which also means I'm going to use Elias not that much, especially announcements. The only thing you can do is send out emails, but then if you signed up for the module late, you cannot see the past emails as far as I know. And whereas CampusWire, if you join later, you can still go through all the old posts and read up on what happened. Okay, exam question gallery, we'll talk about another time. That's all on administration and organizational things. There are questions on this bit. Yeah.
Für welche Sachen kann ich das benutzen? Ich bin Bachelorstudent und auf der Moodle-Website stand, dass ich es theoretisch, also auf der Moodle-Website stand explizit, dass ich es für den Master benutzen kann, aber nicht explizit, dass ich es für den Bachelor benutzen kann.
Sehr gute Frage. Müssen wir vielleicht offline klären. Yeah. The question was what you can use the module for if you're still in undergrad. And I think it might depend. Should be possible to do it instead of one of the other specialization modules. That's my intuitive reasoning, not the legal answer. Was there another question?
No, I just wanted to answer this. As far as I know, master students are allowed to take 18 credits from the bachelor degree and the bachelor,
that way around, yes.
Yes, and the bachelor ones can take 18 credits from the master degree.
I see. Yeah, it would make sense that there's some limit. Although doing harder lectures maybe is fine, right? Yeah. There's also the option of getting an exception from the normal rules if you can justify why. Yeah. Okay. As always, organizational stuff takes more time than I was planning. Let's jump into a little bit of actual content. In Unit 1, I'll give you a brief outline of what the module will cover, and I'll try to motivate a bit why we embark on this journey together. It will resolve around the question of how to solve hard computational problems. And there's a bit of a problem there because they're hard because they're not easy to solve. So how are we supposed to solve them anyways? If you've done a TCS module in undergrad theoretical computer science, you may have encountered the story behind this cartoon, which is taken from, I think the most cited computer science book, full stop. Which is funny that it's a theory book. Maybe this is no longer true and some deep learning stuff is gathered more citations now. It had some time to acquire those citations. Does anyone know the book? By name, have you looked into it? Yeah, has anyone looked into it? It's same as Don Knuth's Art of Computer Programming. It's a book famous to be known and bought, but never looked into. It's a good book, though. It's actually quite accessible, and the writing is very well done, which hopefully is why it got all those citations. The story in there goes: you're tasked to solve some computational problem. You're employed in industry, and your boss tells you solve this problem, and now. And you try to find an efficient algorithm that gets the job done, but you kind of fail. And then that's a bad situation to be in. You would have to walk up to your boss and tell, I can't do it. I guess I'm too stupid. Okay, that's it. A better option is to prove that the problem is NP hard, in which case you can point to this long queue of famous and clever people that try to solve the same problem and also failed. So at least your boss is not going to say, I'm going to hire someone else instead, right? So there's an indication that a problem is hard. That's what NP hardness is all about. It's a formal proof that it's at least as hard as a lot of other problems that a lot of people have tried to solve and all failed in a specific sense. Now, that doesn't really solve your problem, right? It solves the problem of not being sacked. It doesn't solve the computational problem. So the quote from the book is, at the beginning they tell the story with this guy in the cartoon, and then many chapters later they come back to this story and say this is the Bandersnatch problem. That's this fictional computational problem that the story was about. It didn't just go away by proving it NP complete. It's still there and it's still not solved. So what are you going to do? And that's the starting point for this module, really. Whenever you have, this is NP hardness is an impossibility result or a lower bound. It tells you that certain things are supposedly not possible. Now, as always with complexity theory, there's this fat asterisk to it that saying that we don't know whether it's not possible. We just can't seem to find a solution. And unless P equals NP, there is none, blah, blah, blah. All that kind of standard complexity theoretic assumption made. We can't solve the problem. So, but it's an impossibility result, and it's a very specific one. It tells you that this specific problem cannot be solved in the worst case exactly by a deterministic machine and so on. It's very specific, and each of these components you can attack and check if there's a loophole around this hardness result, about the impossibility result, to get something useful. And we'll go through a couple of more or less successful loopholes on a lot of different example problems and see what we can do, or also what we cannot do still. And here are the typical loopholes listed. I'll go through them in a bit slower pace in the next slides. We'll cover the first 4 and not the last one. That's a bit of a personal choice. There's nothing wrong with quantum computers or quantum algorithms. It's interesting theory. We haven't seen a quantum computer that can do anything really useful, so it's definitely still a theory at best. And it's not clear how much they help here, whereas the other examples, all of them have applications where they've proven to be useful beyond the general theory of throwing up your hands can't be done. So what are the loopholes? For each of those, it's essentially some aspect of the impossibility result that we can try to attack. And we'll see what we can do to work around those. So if these are exploit it? What can we do algorithmically? Can we solve the problems if that thing is avoided? Sometimes that's still not possible, and there's refinements of NP hardness reductions that show similar impossibility results, including the loophole now. Even if you take that into account, a problem is still not easy to solve. And that gives us examples where the loophole either works or not. And it's always good to see the two sides of the line. Now for this module, we'll focus on, I called it eternal truths, the things that won't age that quickly. In particular, rigorously provable results, as opposed to specific engineering ideas. There's a bit of a tension there always, so it's certainly more on algorithm theory than on engineering. Both is valuable and interesting, but for this module, there's a clear focus on the theoretical part, with the benefit that the things that we do prove, they're going to be true forever. Right? There's very good reasons why the models that we'll cover later and tomorrow are really going to stand the test of time, and not much is going to move there. And so that's eternal truth knowledge. What it requires is a foundation in math and TCS, as I said, because we'll use the tools of rigorous proofs. Also, at times, I'm picking example problems that illustrate a point pedagogically well, but are not maybe the most exciting application. That's always a trade-off too, and I'm striving for including a bit of both. But the pedagogical examples often come first because they illustrate the technique and allow you to acquire the skill, as opposed to learning a specific portfolio of known solution. So a brief outline of the loopholes that will each be a larger chapter of themselves later in the module. So chapter 0, if you want, or part 0, will be recap on the classic NP hardness theory via the mini seminar and via some lectures today, tomorrow. The first loophole that we'll look at is large integers. Many problems talk about inputs that have numbers as part of them. And sometimes problems are only hard if those numbers are allowed to be really big. And more formally, a problem is encoded in binary at the end of the day in a computer, and even on the formal models that we'll consider essentially the same thing. So numbers are encoded, and there's a difference between the length of an encoding of a number and its value. The value can be exponential in the size of the encoding. Right? If I write down 1,000,000, it only takes 6 or 7 digits. But it's 1,000,000, right? It's a big number, and you can ramp this up more. So the algorithmic idea there is to design algorithms that exploit the fact that you have small numbers only. And sometimes that's good enough. On the other hand, there's also problems where you can show even if all numbers are small, they're still hard. That's loophole 1. Loophole 2 is a generalization of this idea. I called it contrived worst cases, which means the impossibility result says the problem in general cannot be solved efficiently unless p equals np, etc., etc. But that seems to be true for really constructed extreme cases that are unlikely to be relevant. And so that's the idea of fixed parameter algorithms, where on top of the input size n, you decide on another thing that quantifies how difficult the input is. And that's called a parameter, and you analyze those together. It's a very broad theory, very effective in many applications, but also not always applicable. So sometimes you can identify for a problem with a specific parameter that even if that parameter is small, the problem is still hard. That's the intuition. Okay, so that's the generalization. Before we had just large integers. Now we have some large property of the input. And you get to decide what that property looks like. The third loophole is that the classical theory asks for exact solutions only. This only makes sense for an optimization problem, say the traveling salesperson problem. You're trying to find the shortest round trip, and the hardness often comes from asking for the precisely shortest round trip. And in practice, you're often fine with being it 1% slower would hardly be measurable. That's where this part gets at. If you're only interested in approximate solutions, sometimes you can do better. Sometimes you cannot. And the line between those is important to know. The last that we will look at is the idea of randomization. You've seen this in other cases. It also in efficient algorithms makes sometimes life easier to use randomization. But the idea here is that it seems that algorithms fail to solve a problem efficiently sometimes just because they run into unlucky cases. And you really need, again, a contrived input to run into exactly those. Whereas if you throw in a little bit of randomness and unpredictability in the algorithm, the hardness seems to go away. This will be a case where there's a widely believed outcome. I don't want to spoil it now. We'll come to that. So the idea is to use randomness in algorithms and see what you can prove about that not being helpful. That's the 4 loopholes that we'll spend time on. The first one will be quick. The other 3 will be roughly a third of the rest of the time. The goal overall is to enhance the ideas you can bring to bear on an algorithmic problem that go beyond the NP-hard or polynomial distinction, and also teach you a bit about how to prove that certain things are not applicable by proving impossibility results of various forms. As I said, the focus is on rigorous methods. We'll leave outside how to bring those into practice, which is essentially a topic of its own. And here's the rough outline planned. That's where we are. That's what we'll spend this week on. And then after the mini seminar, we'll start with loophole 1, loophole 2, loophole 3, and loophole 4 as a rough indication of the time that we'll spend on. If you look at this, it will not work out that they can each take a week. We don't have enough weeks if we take out the mini seminar, so they'll have to be a bit shorter. But that's roughly the plan. Okay, questions on big picture plan? On this? The big picture plan.
Just a short question.
Yeah.
Slide from Hans is there a link in the course?
I think there's only the lecture notes, which are the slides plus handwritten notes added. Okay. The slides back then, I think my tendency today is to put more on the slides so that they serve as a kind of bullet itemized lecture notes without much writing on them. Back then I wrote a lot more during the lecture, so the slides themselves would probably not be so helpful, but the lecture notes are there. As I said, there'll be some differences in the details, but if you want to have a rough idea, zoom into the future, what will certain of these topics look like in detail, you can have a look at those. Yeah.
What would the exams look like? Would it be the algorithms or the concepts?
Yeah. bit of both. In this module is trying to teach you some skills on how to apply them to a new problem. So ideally, the exam would also cover that a bit. In the time, especially in a written exam, that's actually not easy to do in a fair way, because you have limited time and it's a kind of creative process. I like oral exams much better for this because I can see how far you get and then give you little hints until you get there. And you can still demonstrate your skill on the way by using the hints in the right way. It's much more effective to test than in a written exam. But it'll have to be part of it in some form. There will also be a part of basically knowledge from the lecture, because we'll cover a bunch of problems and techniques where you can just shine also by knowing what we've covered. Well, greetings to Egypt. Brave New World is cool. Is that a rare bad case? I guess the underlying computational problem in gradient descent is finding a global optimum of some complicated function. And the question is, what does that function look like? So you would have to somehow narrow down what that. If you define this on a general, like the general problem, give me any function, high-dimensional function, and you ask me to find a global minimum or maximum, that's going to be a very hard problem with no chance of success, and certainly like a gradient descent. I guess backpropagation is really asking about gradient descent here, and this is minimizing some loss function. We're digressing a bit. I think it's not really understood why gradient descent doesn't fail more often. So in a way, it's yes, it's a rare bad case, but the question is how to model it. In the sense I used the word rare bad case, it was in the context of randomization. I don't think it's random there. Well, yeah, could be randomized, right? Yeah, stochastic gradient descent. Yeah. It's an interesting question. I didn't think about it from that perspective much. So I'm not sure I have some much intelligent to say at this point. Yeah. True. Yeah. Yeah, it's a randomized algorithm in the most useful ways that it's applied. So it could be an interesting test case to look at what randomization could do. I'm sure there's some work on this, but I'm not aware of results there, so I'll stop speaking about it. But it's certainly interesting, especially what the algorithm theory has to say about some of the machine learning algorithms. There's a lot of interest in that. Yeah, I normally try to do a break in the middle of these sessions. The first bit was just organizational blah blah, so maybe it wasn't as exhausting. And we've had a little bit of chit chat now. So I'm inclined to move a little bit into the next unit, because we should really cover most of that basics before tomorrow, so that you can do the mini seminar. So let's try to conjure up some last energy for a few minutes. We started pretty much on time, so I should let you go at 1:45. But let's start a little bit with the complexity theory definitions. Again, I called it recap for all of those, for the 3/4 of you who've done some TCS module, it should be essentially just that. But maybe you've seen the definitions slightly differently. So I wanted to have a solid foundation for the things that follow on, both in terms of you knowing what I'm talking about and also having specific definitions of the models of computation. So I want to focus on this a bit, but also go relatively quick because we're covering something in 1 week that should really be done over the course of maybe 3 weeks in an undergrad module, maybe more. We're not doing all the reductions, so maybe 3 weeks is pushing it, but definitely at 2x speed. So if you find it hard to follow, there's good books that have a bit of more conversational tone in between the definitions. I'll link some of those on the website. I should have brought them here. The problem is there's no book that uses exactly the same definitions. They all have some quirks where I don't feel this is the nicest way to do it. So it's not exactly the same as any specific book. Sorry about that. But we can talk about that offline, why and how things are different. Okay. Let's start with Unit 2, a recap of classic complexity theory, NP completeness. And let's jump right in. So we'll probably just get into some of the definitions for today. I'll give you a bit of a motivation first. That really should be easygoing. And then we'll try to be very careful in defining what a computation is and what the models of computation are that we look at. And then we can define these classes P and NP. There's an alternative characterization that I want to touch on, and then we get into the actual business of NP hardness and reductions. As in all the module, we'll start with some computational problem, which is always of this form that you're given some input and you're asked to produce a certain output. And it turns out that some of these questions just seem to be hard nuts. They seem not easy to solve, at least not quickly or in the usual sense. So always exact and correct and efficient in a specific definition. And here's this example that I brought up before, but let's define it properly. The traveling salesperson problem has as input a list of cities. These are just some identifiers. The real input are all the pairwise distances. So just a big matrix of the distances between any pair of cities. It's n times n minus 1 because it's really without the diagonal, right? The diagonal is just 0. The distance is there. So it's the distance matrix between those cities. We don't make in the general case any assumptions about these distances. That is important. It does not need to be symmetric necessarily. It doesn't need to be a metric. So it doesn't need to reflect the usual assumptions on distances. It could in general be arbitrary numbers in these entries of the matrix. And then the question is, can you find a shortest round trip? Formally, it's a permutation of the cities, and then so I'm just going to write this as SI1, SI2, and so on up to SIN. So the S1 up to I1 up to IN. These are the integers 1 up to n. I'll write this shorthand for the first n integers. So that's a round trip. That's a weird round trip. I'm just listing the cities. But you're supposed to imagine you go through cities in that order, and then you return back to the first one. And so the cost of such a permutation would be summing up the distances that you travel. So you go from city ij to city I, that's the first mistake, ij plus 1, say. Now I arrived at city Sn, so I have to go back. So that's the last summand that was missing. Now I've closed the circle. Okay. So to formally specify the problem, you would have to write it a bit more like this. On this first introduction slide, I didn't do it. Later on, I will. That's the way to make it clear. Now, it seems we don't know how to find the best possible round trip in any meaningful way in this general case. No such algorithm is known, where efficient means polynomial running time in the input size. Again, we'll come to define this formally. So it seems there is no efficient algorithm for this, but that might just be us being incompetent. Can we prove that there is no such algorithm? As you may know, no. There is no proof that there is no such algorithm. The only thing we can do is give strong evidence that supports this hypothesis, but we don't have a proof. If that sounds like not a very strong day for theoretical computer science because it can't answer that question, we can do something. And that's this picture again, as you've seen before, right? We can at least point to the fact that we can prove that it's as hard as some other problem that nobody solved. And how do you do this in complexity theory? I'm staying in this, I'm getting hungry now, but I'm staying with nuts. So that's a macadamia. They're not to scale, right? But if you put them next to the same size, you couldn't see anything of the macadamia. But have you ever tried to crack a macadamia with the shell? They're incredibly hard. Like there's no way, with a normal nut cracker, no chance, right? You need a special screw-in thingy, and then even then, you often end up with the whole nut squished together with the shell. Well, that's me at least. So this is standing for an even harder nut than the cocoa nut, okay? The idea in complexity theory is to compare problems with respect to the hardness of how complex they are to solve. And so we start with an old problem where the conventional wisdom is that it's not easy to solve. And we try to find a new problem, or we have a new problem where we don't know whether it's hard, but we try to find some comparison. We'll denote it by this less or equal p for polynomial time reduction. Again, we'll come to it. The intuitive idea is if A is known as to be a hard nut and B is at least as hard as A, then, well, B is also a hard nut. Okay? And in complexity theory speak, we would say A is NP hard, which means that probably there is no efficient algorithm for problem A. Then we would show this property, which means that B reduces to A. And you can read this less or equal as hardness. So B is harder than A in this specific sense, which means that's basically the definition of this less or equal. If there's an efficient algorithm for B, then there is an efficient algorithm for A. It's this implication. For the experts, that's a slight lie because we're usually doing Karp reductions, not Turing reductions. Yeah, come back to that. But if we take these two things together, like in the picture on the left, we get that B is NP hard. And that again means probably no efficient algorithm for B. That's the picture you should always keep in mind. And in particular, you should use the picture to memorize what the less or equal points, in which direction it points. And you reduce cracking one problem to cracking the other problem. You reduce B to A. No, you reduce A to B. Sorry. Okay. What do these letters P and NP stand for? P is the class of problems for which there is a known algorithm that has polynomial time, which will equate with efficient. So what does that mean a bit more specifically? There's an algorithm that solves every instance, every example of this problem P in a time that is polynomial in the encoding of this instance. Okay. And here P stands for polynomial because that's the running time of this algorithm. And it's the same as asking for an algorithm to find the solution. And NP is the class where the name is not as intuitive. It's the class of problems for which we can, in polynomial time, verify if we're given a candidate solution for an instance. Then in polynomial time, we can check whether it's a correct solution for this instance. So we don't check that it's an optimal solution, say in the TSP problem. We would be given the distance matrix and a specific permutation of the cities. We still have no way of knowing whether that is the best possible round trip. But if you give me the cities and the round trip and ask, is that round trip shorter than some threshold? I can answer that. And that's what this is really asking only for. It's a very weak requirement. So NP stands for historically non-deterministically polynomial. Again, we'll come to that. Intuitively, it's where a non-deterministic algorithm can find the solution. We'll show that these two things, the definition here and this non-deterministic computation, come down to the same thing, even if they at first look different. And so what's this question then? It's obvious that P is a subset of NP. It's most easy to see, maybe for the boxes, if you can solve a problem from nothing, then you can also check if a given solution is easy. You can just forget the solution and basically compute your own. So that's an easy thing to observe. And we think that the inclusion is strict, which means that the two classes are not the same. But again, nobody knows. This is arguably the most important open problem of all of computer science, depending on who you ask, I guess. Some people even include mathematics because many questions in math are maybe more narrow. But okay, this is let's stay within theoretical computer science. I guess there is no discussion to be had. And that's why these classes are so famous. It's the difference between solving a problem and checking a given solution, which intuitively feel really very different. So we've seen intuitively what we want to do with NP completeness. And now we should do the work of defining in detail what we mean by all these terms that I used informally on the previous slides. And let's start with this. You can think about it. I'll set it up just as a oops. I'll leave the slide with the answers. We'll see the results in a second. Should be a few more people in the room than have voted. Anyone still thinking? Let's see the results. And I've allowed various things as correct answers because the point of the question is that it's not a very well-defined question. You could either say it takes constant time because adding to integers, say, what's people's famous most well-supported programming language? Python. Yeah, Python is a really bad example because Python has these built-in smart integers that grow in, yeah. So C and Java, anything that's a bit closer to the silicon makes this point clearer. If you have an int in C or Java, a machine word in the computer, you can add those up in constant time independent on how big the numbers actually are, right? It is true. And with 64 bits or even bigger long longs, it's big numbers in a way. On the other hand, what I mentioned about Python, that if you make the numbers bigger and bigger, they will eventually overflow a single word. And Python is smart enough, or is programmed to be like that it then automatically swaps out the representation of this integer by effectively a string of the digits. And if you do that, then adding up to numbers that are represented as strings of digits, you have to at least read the numbers. So it's going to be proportional to the number of digits no matter what, even if you don't do anything smart. And addition is actually not smart, so it doesn't need to do more work than that. So fine, what does that mean now, right? Shouldn't there be a well-defined answer? That's the point of this question, to get you thinking about this. In this case, there's a well-defined answer. That's the word RAM. We'll come to that. But whenever you talk about computation, and whenever we talk about computation in the context of algorithm theory, we're thinking of asymptotics. We're making things grow bigger and bigger because interesting comparisons are usually only possible for the limit of input sizes going to infinity. But if you do that, you always have to think about these weird questions, inevitably. Okay, to cut the story short there, let's have a look at the solution for this specific case. More broadly in this module, we'll talk about complexity classes, which are sets of problems that have algorithms of a certain kind, or that allow algorithms with a certain efficiency. We had P and NP. P was the class of all problems that have polynomial time algorithms in the simplified version. Now, if we can't even decide on what addition should take as time, how would that make for a sensible definition? How can I classify problems by having some algorithm without saying what algorithms are allowed and what costs they have. And so it's true in general, there is no such universal thing. You have to always say what is the model of computation and what costs do you assign an algorithm. Otherwise, this question makes no sense. And so we have to fix a specific machine model. It turns out that the question of P and NP is very robust against many of these changes and will make sense irrespective of many of the specific definitions. But you still need to pick some of the definitions to get started, and then you can prove that other models are not much different. I think it would be a misunderstanding to say, oh, because P and NP are so robust, which is the outcome of a deliberation with many concrete definitions, it would be a mistake to say, oh, then it doesn't matter to define it properly. Because then some of the other bits where it does depend on details get very, very vague and unclear. So what's a machine model? It defines what is an algorithm. So what are programs? What can I write down as computational recipe? How they are described. Some sort of programming language is usually associated with this. And crucially, what are the costs of an execution? That's also part of the machine model. And this is what I took from efficient algorithms. It should be detailed and powerful enough to reflect what actual machines do, while at the same time unify the specific iteration this year, and hopefully be also simple to analyze. That's often hard to achieve all three of them at the same time. But for algorithm theory, there is a standard model for complexity analysis that gets a good compromise between those three goals. And that's the word RAM, or the random access machine for short. I'll describe the model briefly before we then actually pivot away from it. But I think it's worth having seen this, because this is the solution to how to properly define this cost of addition. Okay? It's also fairly close to actual hardware still, unlike the Turing machine that we'll look at afterwards. So a random access machine has an unlimited memory. You should think of this as being as big as you need it, and when you need it bigger, you just add another piece of memory to your computer. You grow the computer as the need for it to grow grows. So it's unbounded in principle. Any specific computer that you can build will, of course, be finite. But we're studying the limit of making this bigger and bigger. OK, one really big memory with cells of numbers, a fixed number of registers, say 100. Number doesn't matter too much, but it doesn't grow. And then each of these memory cells and registers stores an integer with W bits. And crucially, this parameter W also grows with the input size. That's a key assumption of the model, and that's what makes it sensible. Even though it feels strange to have a machine grow with its input, this is historically what happened to computers. So it's not so absurd after all. So if you have W bits, you can represent numbers in this range. Let's stick with positive integers. You can simulate all else based on that. W is called the word size. That's what W stands for. A word in a computer is just the piece of bits that it can work with in constant time, or in one cycle. And the typical assumption is that this word size grows logarithmically with the input size. This makes sense from different reasons, from different perspectives. It means that you can store a pointer to a place in memory in one word, or in a constant number of words. It means that it also reflects a bit how historically these word sizes have grown. That's what the machine looks like. And then we need to define what programs can be. And these are essentially a low-level assembly language. So there's instructions to read something from memory and write it into a register and write it back. There's operations to compute only on registers. You can do the usual arithmetic operations, and you can do logical operations. And then there's conditional jumps. And that's pretty much it. That's close to a RISC instruction set that some computers have. Intel CPUs are a bit of a mess, but ARM, what's in your phones, is not too far away from this, instruction set like this. I'm defining the model in this detail because now we can answer this question of what should an addition cost? Well, if the numbers are small enough to fit in one word or a constant number of words, it does take constant time to add them up. Whereas if the numbers get bigger, you have to divide the size of the number by W. That's the answer. And the question is, are the numbers part of your input size or not? That's for you to decide when you define the problem. The running time of such a program is just the number of instructions that it executes, roughly the number of cycles if you want. And the space cost is the total number of memory cells that were ever touched. Okay? I think the definition maybe is, depending on how much background in computer architecture you have, maybe it's a natural definition, maybe it's a bit awkward. That's the standard definition that seems to make most sense for studying efficient algorithms. And I guess we'll leave it with some small concrete example what a program here can look like. And the point here is not so much to read this in detail. This is an implementation of bubble sort from Don Knuth's books, which I quoted it earlier as one of those books that many people have in their shelves without ever reading. And I guess one reason is that he writes his algorithms in assembly language that's not so dissimilar to this. I basically could translate his code on his hypothetical machine one-to-one to our made-up RAM machine. And I didn't have to invent more detail. So he studies algorithms really at this low level of detail. We don't normally do that. And we won't do that in this module. What we actually do in this module we'll come to tomorrow. The word RAM is great because it reflects, at least for the CPU cost, lots of actual architectures. Luckily for this module, for the coarse distinction that we are after, polynomial time versus probably not polynomial, a lot of the details in the word RAM model are not so important, and we can get away with a at least theoretically more clean model of computation. Okay, more on that then tomorrow.